This is an introduction to electromagnetic radiation, which is also known as light. I tend to use the term light to refer to all electromagnetic radiation, as some people do. Some people reserve the term light for the visible part of the spectrum. I call that visible light. Light is composed of traveling electric and magnetic fields. We haven't really learned what those are, but electric fields are produced by sometimes moving charges originally, or various other things. But at any rate, the combination of the two is what produces light. Things to describe light. Wavelength is one of the terms we use to describe light. It's the distance from one wave crest to another. And in this case, the wave crests, the waves themselves are electric and magnetic fields, and the distance from one crest to another would be the distance from a maximum of the electric field to the next maximum of the electric field, or the magnetic field. They both have the same wavelength for a particular light wave. The wavelengths are measured in some multiple of meters. It'll depend on the type of wave that you're dealing with. They have a huge range of wavelengths, as you'll see. When we're talking about visible light, we're going to be using nanometers. We'll also use an unusual symbol for the wavelength, the Greek letter lambda, and practice drawing it, I guess, or just get used to seeing it. Here's a sketch. When we show things like this, we almost always show a very simple wavelength. This is something called a sine wave, and it looks very simple. In general, waves can be much more complex than that, particularly sound waves, but it'll still have some kind of a repeating pattern, and the wavelength is the distance from one place on the pattern to when that same place happens to repeat. It's easiest just to look at the crests and the distance between those. Another thing we use to describe the waves is the frequency. That's how many times per second the wave happens to go by, or how many wave crests go by per second. We measure the frequency in cycles per second. You could think of it as waves per second, or just repetitions per second. And a cycle per second is called a hertz, and the abbreviation is a capital HZ. That's a standard practice when a metric system unit is named after someone, is to capitalize the abbreviation. So, more common with light in particular is that we have multiples of hertz. Light travels so fast that many waves will go by per second, and so kilohertz or megahertz or gigahertz are what we might measure the frequency in. A couple of typical frequencies. An FM radio station here in town is 99.3 megahertz. They don't often state the actual unit of the number for the radio station. They'll just say 99.3 or something like that. But FM radio stations are measured in megahertz. So a mega means a million. And a cell phone frequency that's common in the United States is 800 megahertz. We're going to use the letter F for frequency. However, in other books and on some of the YouTube videos that I made available to you, they use the Greek letter nu for frequency, and you pronounce it nu, and it looks an awful lot like a V. The speed of light, all of it travels at the same speed in a vacuum, and nearly the same speed in air. It slows down just a tiny amount in air, but not much. It's still going very fast. And in vacuum, well, that speed is 3.00 times 10 to the 8th meters per second. If you're in air to that many significant figures, it's going at that very same speed. So it doesn't slow down appreciably until you have it going through something like water or glass or something like that. But in here we're going to be mostly interested in light that's traveling through air or vacuum. So we'll just use 3.00 times 10 to the 8th meters per second. The speed of light is actually an exact number. We define it to be 299,792,458 meters per second, and the meter is defined in terms of the speed of light. It became possible to measure the speed of light more precisely than you could measure the distance between two scratches on a platinum bar, so the meter was redefined in terms of the speed of light. And the frequency, wavelength, and speed are related by this equation. C is the abbreviation for the speed of light because in Latin celeritas means fast or speed, and light does go fast, so that's why we use the letter C for it. But C is equal to F lambda, so that's a nice tidy relationship. That means because C is a constant, if you increase the frequency, the wavelength must get smaller because the two have to multiply together. If you decrease the frequency, the wavelength must get larger. And here's the visible spectrum. Convenient units for visible light are nanometers. It ranges from about 400 nanometers on the violet end of the spectrum to about 700. And a nanometer means 1 times 10 to the minus 9th meters. And you can see the range of visible light there. They're only approximate. It can vary from person to person. Some people don't have the ability to see particular wavelengths. I don't think I can see all the way down to 400 nanometers. I'm not sure I ever could. I can remember doing an experiment, and of 5 of us in the class, only 1 person could see down to 410 nanometers. So it varies a bit. The way you might determine a frequency is, if you could, count the number of waves that happen to pass by in a second somehow. It wouldn't be particularly easy, but an electronic instrument might be able to do that. Is there light that we can't see, or electromagnetic waves that we can't see? Are there wavelengths longer than 700 nanometers or shorter than 400 nanometers? Yes, there are. Here's a kind of sketch of the complete electromagnetic spectrum. And the shortest wavelengths are gamma rays. Up here at the top end of this, these are the very shortest wavelengths. A millionth of a nanometer, 10 to the minus 6th is a millionth. And there's a range for all of these. The divisions between X-rays and gamma rays, those are just man-made selections that we've made. It isn't like there's any definite wall between gamma rays and X-rays. It's just we chose some spot to say that, okay, these are gamma rays down here and these are X-rays down here. Similarly with any of the boundaries between these things, ultraviolet radiation and X-rays. Now in the case of visible light, there is kind of a definite cutoff for a particular person's eyes where they stop seeing visible light for short wavelengths or visible light for long wavelengths, but that varies from person to person, so all of these boundaries are approximate. But they're generally pretty good. Infrared radiation has longer wavelengths than visible light. Microwaves are longer still, and then you get to the radio wave part of the spectrum. And in all of these particular divisions, there are also finer divisions. So in the radio wave spectrum, you have AM radio waves, FM radio waves, and various things. Finer divisions still. Which part has the longest wavelength? Well, not up here. These are very short wavelengths. Anytime you've got a negative exponent on something, that's pretty short. Down here, longest wavelengths, 100 kilometers. That's more than 60 miles. So that's a long wavelength. Which part has the shortest wavelength? Well, we've already talked about that. That's up here for the gamma rays. So that's where the shortest wavelengths happen to be. Is there a simple relation between wavelength and frequency? I've already stated it once, but there's the equation, C equals F lambda. But here's a way of stating it. The longer the wavelength, the lower the frequency, and the shorter the wavelength, the higher the frequency. So that's a nice way to remember it. Here are some examples with the equation C equals F lambda, and I'll show you how to do calculations with these. For instance, what's the wavelength of the radio station you listen to? Let's suppose that the wavelength has a frequency of 91.5 megahertz. Right? Well, the equation we'll use for this is always going to be the C equals F lambda, and things that we know for sure is that C is equal to 3.00 times 10 to the 8th meters per second. I think on one of these problems I may use more significant figures on that because we're given a wavelength to more than 3 significant figures. But in this case, the frequency is that many megahertz. We want the wavelength. So if I solve for the wavelength on here, I would get lambda is equal to C over F, 3.00 times 10 to the 8th meters per second, and the frequency here, 91.5 mega. That particular metric abbreviation means million. It means you can replace that letter with times 10 to the 6th. And so that's what mega means. Now, a hertz is a cycle per second. And unit-wise, if you look at the top and the bottom of this, the top has a per second, the bottom has a per second, and so those actually divide out, and I'll have meters per cycle when I get done with this. And the cycle is just a placeholder word. It's something that they wanted to stick on top of the fraction so you didn't lose track of it. And so it's really just meters when you end up with the wavelength. And the way I put those into my calculator, I would just go 3.00 on this one, EE8. This is a nicer calculator for scientific functions than a lot of them. And then divided by 91.5, and then a 6 there. And I get 3.28 meters for the wavelength of that. 3.28 meters is roughly 3 giant steps that you might take. So as this FM radio wave is traveling past you, if you could stop it, you could stand at one spot that might represent the maximum of the electric field, electric and magnetic fields for that radio wave, take 3 giant steps, and you'd come to the next place that the electric and magnetic fields have their maxima. Of course, the wave is actually traveling along at this high speed here, which, by the way, in American units happens to be 186,000 miles per second. So it's going at a pretty good clip. Okay, another problem that I had you do on there was to calculate the frequency of the instructor's laser pointer, which is about that much. And so here we know the wavelength and we're after the frequency. This is in the visible light spectrum. It looks red. And so that N in the metric system means nano. And when we see that, we can replace the lowercase n with times 10 to the minus 9th. So 633 times 10 to the minus 9th meters. Okay, well, again, we have C is equal to F lambda. This time we want to know the frequency, so we divide both sides by lambda. So F is going to be C divided by lambda, which will be 3.00 times 10 to the 8th meters per second divided by 633 times 10 to the minus 9th meters. And I'm going to call this meters over 1 just for the heck of it. Unit-wise, when I look at the units, I'll have meters per second on top and meters over 1 on the bottom. When you divide by a fraction, you invert it and multiply, so I'll have 1 over meters up here, and the meters go away and I'll have 1 over seconds, or per seconds, but that's where we put in that placeholder word, cycles per second. So we'll end up with that. And on this one, I'll have 3 times 10 to the 8th divided by 633, 10 to the minus 9th. By the way, I have some videos available on learning to use scientific notation on your calculator, things you may want to refer to. And I get about 4.74 times 10 to the 14th hertz, okay, or cycles per second. And so as long as I have my speed for light in meters per second and my wavelength in meters, I'll get my frequency in hertz. And I'm sure you could write that as something like, let's see, megahertz, gigahertz, terahertz probably. It's probably 474 terahertz, but I don't know that I've ever heard anybody use that particular abbreviation with that one. It's nicer just to call the wavelength 633 nanometers. Okay, this happens to be a famous wavelength in astronomy. It's one that's given off by neutral hydrogen, and it's a way that we can map the location of hydrogen in our own galaxy and in other galaxies and surrounding galaxies and between galaxies. There's a lot of neutral hydrogen out there in space. And a centimeter, that means 10 to the minus 2. It's 1/100th of a meter. So another way of writing that wavelength is 21.106 times 10 to the minus 2 meters. And again, we'll be using C equals F lambda. It's the frequency we're after. And so the frequency will equal C over lambda. Unit-wise, this is going to be identical to the last one we did. So 3.00 times 10 to the 8th. Actually, I'm going to write this instead as 0.9979 times 10 to the 8th meters per second. I've got 5 significant figures here, I've got 5 here, and so I'll be able to keep 5 significant figures. So 21.106 times 10 to the minus 2, minus 2, let's write that legibly, meters. And again, meters over 1, or meters per cycle, you could call it if you wanted to. Anyway, that frequency will end up being now this would be 10 to the 9th is giga, so this would be 1.4204 gigahertz. And a few years ago I took a course in radio astronomy at the Green Bank Observatory in West Virginia, and I always thought everyone would refer to this as the 21 centimeter line. but they referred to it as either I can't remember if they referred to it in gigahertz or if they converted this to megahertz. This would be 1420 megahertz. So they referred to the frequency, and apparently that's something that they do in radio astronomy. So there's some example calculations for these things. Now, why should we care about wavelengths and frequencies of light that we can't even see? Well, astronomical sources give off all parts of the spectrum, from gamma rays to radio waves, and including gravity waves now. So by studying everything we can, all these different wavelengths, we learn a lot more. Some things give off only radiation outside the visible spectrum. So if we weren't looking outside of it, we wouldn't even know about those things. And some sources give off a whole bunch of wavelengths. And to get a complete picture of what the object is doing, you need to look at all those different wavelengths. And I put look in quotation marks because if we can't see them with our eyes, we have to use other instruments to do that. But there is a problem, and that is Earth's atmosphere blocks many of these wavelengths. This is a figure that shows for the Earth's atmosphere how well different parts of the spectrum get through it. There's a visual window that happens to let visible light through. Our eyes probably evolved the way they did because our atmosphere lets through light of these wavelengths, and so they became sensitive to those wavelengths. There's also a radio window, radio wavelengths that get through there. Interestingly, what we think of as things that travel through the atmosphere just fine, FM and AM, are actually somewhat blocked by it and don't get through it so well. It's a good thing that gamma rays and X-rays don't get through the atmosphere very well, because those are very high energy particles when we talk about particles of light, and they have enough energy to pass right through your body and ionize atoms all the way through, which you don't want happening if it happens to be in the reproductive machinery of a cell. It could trigger cancer. So you don't want to be exposed to gamma rays and X-rays any more than you absolutely have to. Here's a photograph of a small region in the Carina Nebula, and it's about 7,500 light years away. And these are dust clouds, and they're being shaped by the light from stars. Light actually exerts pressure on things like dust clouds. And this photograph is invisible light. This is a photograph of the same region, but this is in infrared light. And the infrared light penetrates those dust clouds just fine. And so we see a picture of more about what's going on there. Here's a picture of a familiar object. This is Jupiter in visible light. This is Jupiter in radio wavelengths. If we weren't looking at Jupiter in the radio part of the spectrum, we wouldn't even know about all this crazy electromagnetic activity that is going on in the regions surrounding Jupiter. So that's why we look outside the visible spectrum.